Hello everyone. In this video, we'll be talking about our paper titled Wide to Long, Learning Lens Compression and Perspective Adjustment for Wide Angle to Telephoto Translation. We all know that different lenses capture the same subject very differently. A wide-angle lens provides a broader field of view and is great for capturing landscapes, whereas a telephoto lens has a narrower field of view and is ideal for portraits or distant subjects. However, smartphones, which are the most widely used camera devices today, are usually restricted to wide-angle lenses because of cost and spatial constraints. Higher-end phones might include both, but that might add to the bulk and expense of that model. Our goal is to digitally generate the visual effect of lens compression in telephoto lenses from just a wide-angle image as input, without any additional optical tools or devices. Lens compression refers to the visual effect where, as focal length increases and the camera moves farther away, the main subject stays the same size, but the background appears enlarged and the foreground appears diminished. This phenomenon cannot be replicated by a digital zoom, which only crops and enlarges pixels. It doesn't change perspective. So our objective is to learn and simulate true optical lens compression digitally from a single wide-angle image. A few related areas of research exist, but none directly solve our problem. Dolly zoom generation methods simulate camera motion effects, but they don't provide any means to learn the amount of lens compression required in the target image. Closer to our work is wide-angle portrait distortion correction, where existing methods adjust the perspective distortions in facial geometry using 3D modeling or GAN-based techniques. However, these are limited to facial images and don't generalize to arbitrary scenes. So our work fills this gap, offering a general, learnable framework that mimics telephoto characteristics across diverse scenes. Our proposed pipeline, called wide to long or W2L, takes a wide-angle image as input here and outputs its telephoto style version. It consists of 4 major stages: the depth-based layering stage, the layer-wise in-painting stage, followed by the inter-layer redundancy removal stage, and the layer scaling and flattening stage finally. Each stage is guided by parameters predicted from a convolutional network we call the image-to-param or I2P network. Together, these modules simulate the geometric and perceptual transformations that occur during actual lens compression. The first stage, or the depth-based layering stage, decomposes the input image into multiple depth layers using a depth map predicted by Midas. Each pixel is assigned to a specific layer based on its relative distance from the camera. This lets us separate the scene into foreground, background, and middle ground layers so that subsequent stages can treat them differently, mimicking how a real lens compresses objects at varying depths. But once the image is layered, occluded areas become visible as gaps between layers. To fill these regions, we use Llama, a state-of-the-art in-painting model based on Fourier convolution. Instead of naively in-painting each layer, we construct contextual masks and in-painting masks that define where and how the model should fill missing information. A dilation parameter, denoted as lambda, ensures that enough surrounding context is available. This parameter is predicted automatically by our I2P network, making the process data-driven and adaptive. When layers are in-painted independently, redundant pixels may appear in overlapping regions, causing visible artifacts after scaling. We address this through inter-layer redundancy removal, computing difference maps between adjacent layers, and applying sigmoidal thresholding based on 2 parameters, alpha and t, which are predicted by the I2P network. These parameters control how strongly overlapping regions are to be suppressed, resulting in smooth, consistent transitions across depth layers. Finally, we perform layer scaling and flattening, which is where lens compression truly happens. We first identify the subject layer containing the main focus of the image. Each layer is then scaled exponentially relative to that layer using a parameter gamma, which is predicted by the I2P network. Layers deeper than the subject are magnified, while those closer to the camera are diminished, mimicking how increasing focal length visually compresses depth. All layers are then overlaid and flattened to form the final telephoto image. All the key parameters lambda, alpha, t, and gamma are predicted by our image to param network, which is a convolutional neural network that takes the input RGB image along with its depth map as a 4-channel input and predicts these values through separate training runs. This allows the pipeline to adapt dynamically to each scene, achieving optimal results without manual tuning. To train and evaluate our system, we create a new wide to long dataset. Each pair consists of a wide-angle source image and a corresponding target image captured with a longer lens, with the camera distance adjusted so that the subject remains the same size in both images. We capture 600 pairs in total, 500 for training and 100 for testing under controlled lighting and camera settings. We also include synthetic data in our dataset generated using image rendering platforms and online tools, ensuring consistent focal length ratios and depth diversity. Our model performs strongly both qualitatively and quantitatively. Compared to naive baselines like UNet or the dolly zoom approach, wide to long achieves more accurate and perceptually realistic results. Visually, W2L preserves the subject shape and background realism while effectively compressing depth without introducing artifacts or distortions. We also evaluate our pipeline on the Caltech Multi-Distance Portrait Dataset or the CMDP dataset to see if it can handle portrait distortion correction, a special case of lens compression. W2L successfully corrects exaggerated facial features caused by wide-angle lenses, performing comparably to or better than existing methods. This shows the flexibility of our method beyond general scenes, extending to portrait photography as well. We further test W2L on images in the wild, which are ordinary photos collected from the internet, and the model generalized reasonably well. We also show that the currently trained W2L pipeline, which is trained to generate lens compression for target focal lengths which are twice the source focal length, can also be used iteratively to accurately generate higher orders of lens compression. We conduct ablation studies, and this reveals that the layer-wise inpainting is the most crucial component, followed by the dilation and redundancy removal parameters. Removing these significantly degrades image quality, proving that each module contributes meaningfully to the overall realism. Thank you for watching.